Hello.
Yes, Rose, how's it?
I'm fine, thanks. And how are you? Can we
No,
we
I'm
at least
doing
do
okay.
paper two?
At least paper
Let's do
two.
paper
Why
two.
do you want me to do paper two? Why? Give
I
me a
got
reason.
19 out of 100. Got him two.
19
Got
out of
paper
100.
two. Yes.
Yo, but it seems like you're having a blast of a time there with that 19 that you are enjoying. You are having the time of your life.
No, I'm not happy. I'm not
You're not
happy.
happy.
I'm just kidding. It's not 19,
What's
but
the
I'm not
cause
happy
of
with
your
my
anger?
marks because. Huh?
You're not happy with your mark because I'm listening.
Our teacher is not teaching us. He said he don't know geometry, Euclidean geometry, so he won't teach us. So I tried. I asked my brothers and sisters to help me. They did, but the marks. Yeah.
You asked your
At
brothers
least
and
let's
sisters to
let's do
help you.
paper two. Only 2 months to go. 2 months to write our final exams. Thank
Hey, I know, I hear you. I hear you. I hear you very well. I hear you very well. So you see now in term, what is it? In this current term that you are in, you will be doing topics that have paper two in them. Grade 11, right? Yeah, Kimberly.
Sir.
You are in grade 11, right?
Yes.
Yeah. So what I'm saying is that in grade 11, you will be doing some paper two aspects in the topics that you'll be covering this term. Yeah. But you guys have a problem with paper two. All of you. Everything.
Only Euclidean and Euclidean in the
That's very
marketing. That's the problem. It has a lot of marks.
yeah. Well, the thing is, Euclidean does have a lot of marks, but also it's also true that it has a lot of marks. So let me ask this first question. If you're asking me for help in Euclidean geometry, do you know all the theorems?
Not all of
Do
them,
you
but
know
I know
all
some
the
of them.
theorems for Euclidean?
No.
Yeah, you see the fundamental problem will start there. The problem will start
Marangere
there
is
if you
possible
don't know
to
the
solve
theorems.
something. Like,
It's possible to what?
not to know the theorem, but to solve them. It's possible.
I want to show you something here.
Yo,
That's a question the Euclidean. Hmm? Can you complete the statement for me? Maybe you can complete it. The sum of the angles around the point is
360.
oh okay. At least you know that. If you know that, then that means you are not far off, Moss.
Oh, around the point, I say, but 360.
Yeah. So yes, you are correct. The sum of angles around the point is 360 degrees. All right. All right. The statement here. Look at this. We're gonna look at this diagram. You're gonna help me find the values, and you're going to give me the right reasons. So I'm depending on you. My life depends on you. Look at the statement. In the figure below, we are told that O, you see O. Yeah, center of the circle. K, K, L, M, and N. K, L, M, N. Now it's 1, 2, 3, 4. K, L, M, and N are what? They are points on there. You know most this word.
Circumference.
Yeah, circumference. What is the circumference? What is the circumference?
I can explain as well, Mara. KLM and N. Circumference.
No. K, L, M, and N are points. They are points. K is a point, L is a point, M is a point, N is a point. Do you know what a point is? Yeah. K, L, M, and N are all points. But where are they? Where are they located? They are on the circumference of the circle. So the circumference of the circle is simply the outer edge of the circle. So you see this circle are what we refer to as the circumference. The distance around the circle is what we refer to as the circumference. Okay. So far, are we together? Okay. So we're told firstly that O is the center. Now the center is also a point. All right. O is the center of the circle. So there's O. Then K, L, M, and N are points on the circumference of the circle. And then there's further information given. We are told that such that LM, you see LM?
Yes.
And you see MN? We are told that they are equal. And you can see the symbols that show the equality of the two lines. Yeah. Then we are told that angle LON is 100. Let's go. LON. So this angle here, 100 degrees. So far, so good.
Yes.
Yeah. Now, listen to me now. This statement here is full of so much information. Just by looking at this statement, there's a lot. If you know your theorems, Primrose, you are looking at this and you're like, yo, so much meat, so much meat, so much meat. What is another word that we say? You see ML, what is ML? ML is also called a what in geometry? From M to L, this line here, we refer to it as a what? Yes, it's a chord. I can nice. I must, you know stuff, must. So if you know all this stuff, then I don't know why you're saying you're having a problem. Right? Now I'm coming here for 2 marks. Determine with reasons the values of the following O2. So K01 low, we want O2. So can you tell me? Angle O2. This angle. From here all the way.
Angle around the point. 360 minus 100
Which is?
equals to 260.
Which is equal to 260. What's your reason?
Reason, okay,
Yeah.
angle around the point.
Angles around the point. Nice. Okay, nicely done. Yeah. So you've given me my first answer, Mna. I did not tell you anything, Mna. I'm just asking you. You are telling me. You are the one that's saying the right things. Okay. 10.2.2. We want to know what is angle M1 plus angle M2. In other words, we want to know what the entire angle, LMN, the entire angle, what is the angle M1 plus M2? Giving reasons. For 2 marks again. Okay, remember now you have new information. You said when this angle, you said it's what? What did you say this angle is? O2?
260.
O2. You just told me what O2 is, angle O2.
It's 260.
Oh, okay, 260. Thank you. Right, now I want angle M1 plus angle M2. This entire angle, what is it?
LM equals to MN. I say 100. I say 100. Negative.
So that means you have forgotten.
I'm still checking.
Okay, no, that's fine. Remember, what did we say this is?
260.
I'm saying the point here. We said O is the...
Center.
Do you remember your center theorems? There are theorems that relate to the center. Do you still remember them?
Yes.
Okay, I'm listening.
Angle at the center equals to twice angle at the circumference.
Hey, so what are you telling me then about angle M1 and angle M2?
100. Get two. Or come on. Half 100, 260. Okay.
Hi guys.
Hey,
130.
130.
Want to prove?
Yeah.
Which theorem want to
It's
prove,
100.
bro?
Okay.
It's 260 divided by 2.
Uh-huh.
Which is 130.
Oh, nice. How did you know it's 130? Because a few minutes ago you didn't know. Now you knew all of a sudden. Who's helping you?
Because
Yes.
of the theorem.
The theorem.
The theorem of the center.
The theorem of the center. Okay. All right. All right. So that's correct. That's correct. Minente, how are you, sir?
Yeah, I'm fine. How are you doing?
We are good. Baba. We are good.
What theorem are you proving? You are proving angle O or you are proving M1 to M2?
No, we were checking angle M1 plus angle M2.
Yes.
And so, do you have any thoughts that are different from what Primrose has just shared?
Yes.
What were you going to say?
I can see. Want to prove angle N1 plus M2.
Angle M1 plus M2, yes.
Yes. Okay. We got the angle at the center.
Okay.
Do you see that?
I see the angle at the center. Which one? This one. Angle O1.
Yes, O1.
Okay, yes.
Yeah. And we have the Kusan isosceles. Do you see LMK?
MK,
L
yes. I see MK. LK,
LMK.
yes.
Yeah.
Uh-huh.
Yes. I want to check my theorems first. What I got is we don't have a cyclic quad here.
We haven't been told explicitly that there is a cyclic quad from the statement.
The way you are putting your phone on the statement, I don't see.
Yeah, there's no cyclic quad.
Yes. But we have LM and MN.
That's true, yes.
They tell us is equal to LON is equal to 100. Okay.
Yeah. LON,
Oh, yeah.
the angle here is 100.
Yes. Okay. Let me check.
So Minentle, Primrose already answered the question. I just thought maybe you had another thought about the question, all right? Primrose first answered the first question and said angle O2 is 160 degrees. When I asked her what's the reason for saying O2 is 160 degrees, she then said angles around a point, all right?
Yeah.
And after finding angle O2, Primrose then went on to say that angle M1 plus angle M2 is 130 degrees. When I asked her why is that the case, she then said to me, angle at the center is 2 times the angle at the circumference.
Yes.
So since this is 260, then that would
Yes.
mean this is 130. She said 260 divided by 2, which gives us 130 degrees.
Yes.
So that's what she said. I thought maybe, as someone who requested, maybe you saw something else that is different. That's why I gave you a chance to actually share what you thought.
Okay. Let me go in the comment section. I want to do a question first. I'm gonna come.
No problem, my man. No problem.
Yeah.
Thank you. So Primrose, back at you. Now, I just want to, for a moment here, look at what we have just actually been exposed to. So hopefully, guys, with the theorems, we know first and foremost that if we have angles around a particular point, these angles that are around a point, if they complete a full revolution, we say that all 1, 2, 3, 4 angles, let's just say this was X, Y, Z, and let's say P. We would say X plus Y plus Z plus P is equal to 360 degrees. And our reason, very important, that we try and use the reasons that are stated in the acceptable reason document. We would say angles around a point, or we can say angle in rev. The thing is, there's the alternative short form reason that we can use if we fail to use angles in a rev. So we can either use angles around a point or angle in rev. So that's very important whenever we are using the idea that angles around a specific point that form a revolution add up to 360 degrees. So that's something we've utilized in our diagram, okay? And that relates to something we should have learned in grade 8, 9, 10. If you are in grade 11, you should know this without a shadow of doubt. Now, the second thing that we've picked up on here is what we refer to as our center theorems. I asked Primrose at the beginning, before we answered this question, I asked her the question that, Primrose, do you know your theorems? All right. And what I want to say to all of you that are listening to me, you guys, if you want to become experts in Euclidean geometry, you need to train and develop your geometric eye. What do I mean by that? What I mean by that is you need to understand first and foremost what the theorems state, what is the condition of each theorem, and then what is the conclusion you can make based on the condition of each theorem. So for instance, for our sender theorems, I want to step into this theorem that we've just spoken about. All right, the one that says the angle subtended by an arc of a circle, the angle subtended by an arc of a circle at the circumference of a circle. The angle subtended by an arc of a circle at the circumference of a circle is equal, at the center, subtended by an arc of the circle at the center, my mistake, is equal to twice the angle subtended by the same arc at the circumference. So, simply put, we are saying the angle subtended by an what? By an arc. Now, we are going to unpack what an arc is. By an arc of a circle at the center of a circle is equal to, or let's say is twice, let's say this is equal to, is twice, or we can say double, is twice the angle subtended by the same arc at the circumference. So, diagrammatically, there are three diagrams that assist us with this theorem. The first one, I tend to say to my learners that the first one is what we call a arrowhead, right? Arrowhead, okay? This is the center, right? This here, from here to there, is what we refer to as an arc, right? This arc is directly opposite this angle. So we call this the angle subtended by the arc. The same arc will also subtend the angle at the circumference. Right? So the angle at the center that the arrowhead has is this one. This is the angle at the center we are talking about. It is subtended by this arc. In other words, it is opposite this arc. Okay? The same arc also subtends the angle at the circumference. So the arrowhead diagram, we refer to this as a center theorem. All right, and it actually represents this statement that the angle at the center, but this angle at the center must be subtended by an arc, all right? And the same arc must also subtend another angle at the circumference. So that's why we say this angle at the center is twice the angle at the circumference. So we have the arrowhead diagram. That's one of the diagrams we need to be familiar with when it comes to this theorem. The second diagram we need to be familiar with is what I refer to as the diamond. Okay, usually call it the diamond. All right. Also here, you have an arc, all right? From here all the way to there, that is an arc. Then this arc subtends an angle at the center. Which angle? This one. Not this one. This one. This arc, okay, subtends this angle. This arc is directly opposite to this angle. And the same arc will subtend an angle where? At the circumference. So this angle. So we say that the angle at this center, all right, this one, this angle specifically, is twice the angle at the circumference. All right. The diamond, the arrowhead, the center angle, the center angle. Okay. Then we come here. The last diagram is the butterfly. I usually refer to it as the butterfly, but some people say it's the bow tie. Okay. But it's the bow tie whose center. All right. This here, this now is the arc we are talking about. The arc. The arc here subtends this angle at the center. The very same arc subtends an angle at the circumference. So it's this angle at the center, which is twice the angle at the circumference, that angle at the circumference being that one. Okay? So this arc, the arc subtends an angle at the center, the same arc subtends an angle at the circumference. Okay? So all of these, whenever we utilize them, we use this reason. Angle at center equal to 2 times angle at circumference. And this is our acceptable reason that we utilize whenever we have to use this theorem. Okay, because its condition is that the angle at the center, which is there for this diagram, which is there for this diamond diagram, which is there for this bow tie diagram, is equal to 2 times the angle at the circumference, which is there for the arrowhead, which is there for the diamond, which is there for the bow tie. And here's the thing, guys. Something very interesting for me is that whenever you see the diagram of angle at the center is 2 times the angle at the circumference, this is what you need to note. 1, 2, 3 are at the circumference. 1 is at the center. 1, 2, 3 is at the circumference. 1 is at the center. 1, 2, 3 is at the circumference. 1 is at the center. So this bow tie is special because this one will have 1 of its vertices at the center, whereas the other 3 are at the circumference. 1 at the center, 3 at the circumference, 1 at the center, 3 at the circumference. That's how you can identify angle at the center is 2 times angle at the circumference. So we come back to this diagram. You relate back what I've just spoken to you, and you try and help yourself see why it is that we said, look, this is the diamond, LMN at the circumference, 1 at the center. Which angle? This is the arc. Arc LN, okay? It subtends an angle at the center, this one, the one that we found, the 260 degrees that we found. And then we say that 260 degrees, all right, if we want to find out what angle LMN is, in other words, M1 plus M2, it would mean that we are going to half 260 degrees and get 130 degrees so that we can locate or actually find the value of the angle, which is angle M1 plus angle M2. So I am emphasizing that point because, guys, you need to know your theorems. You need to know your theorems and you need to understand how they relate to the respective diagrams. If you don't, if when you hear of angle at the center is 2 times the angle at the circumference, you only think of this diagram and you don't know this one and that one, hey, you are going to fall short. All right? You're going to fall short and you will not be able to see what you need to see in a diagram so that you can answer questions. All right? Because you'll be looking at this and all you'll be seeing is all these lines and all these circles and they don't really make much sense. So that's why we need to then go back to what? We need to go back to the theorems and make sure we understand each theorem, each statement, unpack it, know the diagram, and then be able to relate the diagram to a specific situation and scenario so that we can unpack the answers that are waiting to be actually found. Okay? So I know that was a sort of like very long explanation. It's like, hey, this guy likes talking, like, yeah, I know. But at the end of the day, this is one of the keys to unlocking Euclidean geometry. If the theorems are not there, it's like, I don't know, it's like a soccer player going into a soccer field without a pair of playing boots and expecting to actually be there to play. No, you won't be able to. You won't be allowed to play. You know, it's like a soccer player going into a soccer field without knowing the rules of the game. I mean, really? No, guys, you know. So there are things that you need to ensure that they are there. So the knowledge is so important. You need to go back to those basics, understand the theorems, know each theorem's diagram, and know what the implications are for using each diagram and the result that you get when you are utilizing each theorem. So hopefully you guys get my point. It's very important. Primrose, let me get you back. Look, come back. You must answer the rest. They are waiting for you, these questions. They are burning for you. So already now we have 260 because of you. We have 130 degrees because of you. Our reasons are popping. Everything is sweet. 9 marks is coming. Yeah, we want angle N1. I'm sure you've been thinking long enough now. It's time. N1. There is angle N1. Waiting patiently to be answered. You now have filled in your information. You have 130 there, which is sweet. Yeah, so I want angle N1. I'm listening. Okay, anyone who is in the comment section and you are looking at this question, guys, we found angle O2. It was 260 degrees. We used angles around the point to find O2, which is 100% correct, because 100 plus 260 gives us 360 degrees angles around the point. Then we found angle M1 plus M2, because angle at the center, which is 260 degrees, the angle subtended by this arc for our diamond, okay, is going to be 2 times the angle at the circumference. So that's 130 degrees as a result, okay? Angle at the center 2 times angle at the circumference. Now, we want angle N1. So my question to you, and what question you should have, is where is N1? Angle N1 is where? It is there. That's where angle N1 is. But angle N1 is part of what? This triangle. What kind of triangle do we have here, guys? N1. N1. NLM. What type of triangle do we have here? Omi, you're there in the comment section. MN is equal to NL. Yes, this is an isosceles triangle. You are right. So, if it is an isosceles triangle, what theorem statement that makes sense can we state based on that knowledge? since this is an isosceles triangle, since ML is equal to MN, what can we then say? Talent, very good. Talent is saying we can say N1 is equal to L1. What is the reason for that? And that's true, guys. You can say angle N1 is equal to angle L1. What is the reason for saying that? Because we need a reason. We can't just state that. Thick-Lerato says opposite angles equal sides. Okay, yeah, let's remember that it would obviously be, I know the wording there, but I get your point, Thick-Lerato. It's angles opposite equal sides as per the acceptable reason document. If we say angle N1 is equal to angle L1, then we say our reason, angles opposite equal side. Okay, otherwise, Thick-Lerato, I get your point. Okay, but it's angles opposite equal sides as per the acceptable reason document that we have available to us. And that's what obviously, these markers, they go by come grade 12, end of the year. So we need to subscribe. We can't just say isosceles triangle. No, angle N1 is equal to angle L1. Reason, angles opposite equal sides. Then after that, what can we then say, guys? If angle N1 is equal to angle L1 for this triangle that we have here, where we know the angle here is 130 degrees, what then can we then say, guys? If angle N1 is equal to angle L1, and that is 130 degrees for this MLN, the triangle, what then is angle N1 equal to? Primrose is saying 65. How? How's that? Explain yourself. Remember, this is like me taking that triangle and actually splitting it, okay? So we've just said this triangle MNL is an isosceles triangle, okay? So if it's an isosceles triangle, then what we can state is that angle N1 is equal to angle L1, as has been stated. The reason, angles opposite equal sides. We are in agreement, most. Okay, angle N1 is equal to angle L1. But we already found that this is 130 degrees. Okay, so typically we can then say that angle N1 plus, right? Remember, we can use, we can add these two angles, but when we add them, we could say N1, angle N1 plus angle N1, because we know that L1 is equal to what? To N. You can say angle N1 plus angle N1 plus 130 degrees is equal to what? 180 degrees. What's the reason? Now, obviously, you can use a variety. You can say angle sum in triangle. You can say sum of angles in triangle. Or you could use interior angles of triangle. You choose. You have a buffet of choice when you have that. Okay, Star Christie, I believe you did indeed. Okay, I believe you did indeed. All right. So please, guys, remember, we said angle N1 is equal to N1. So these two angles are equal. Young Grootman, yes, I saw you there. Angle N1 plus angle L1 plus 130 is 180 degrees. Okay, 130 degrees is 180 degrees when we add. So if we add now, you can say angle, it's 2N1 plus 130 degrees equal to 180. We transpose our 130. We get 50 degrees. Okay, and then what do? We divide both sides by 2. So angle N1 is actually equal to what? 25 degrees. Okay, not 50, but 25. Okay. And I want you to understand, guys. I want you to understand. Remember, we got that M1 plus M2 is 130. LMN is at what? A triangle. What do we know about the interior angles of a triangle, the sum of the angles in a triangle? We know they add up to 180. So if this is 130 and we are told that this is an isosceles triangle, it would stand to reason that if angle N1 and L1 are equal, then we can write angle L1 in terms of N1. So we say angle N1 plus angle N1 plus 130 is equal to 180 degrees. Reason? Angle sum in triangle, you could write that. Or you could say sum of angles in a triangle. Or you could say interior angles of a triangle. Okay? Then we go ahead and we solve for angle N1. And when we do the mathematics, guys, it's a beautiful, sweet solution whereby we're able to get angle N1. It is 25 degrees. Okay. And guys, once again, where are we getting this information or knowledge from? The fact that angle N1 is equal to angle L1. This is coming from the grade 9 and grade 10 syllabus. Grade 8 already, when we did triangles, we learned about the fact that if we have an isosceles triangle, the relationship that exists between angles exists because we say the angles are equal. Why? Because they are opposite sides that are equal. So that's why we say angle N1 is equal to angle L1. Reason? Angles opposite equal sides. We do not use the reason isosceles triangle. It is not a reason that we use. We use the reason that the angles themselves are opposite what? Two sides that are equal. Hence we say the angles are equal. Right? Then if you're going to add the angles of the triangle themselves, you can say angle N1, which is the angle that we want, plus angle L1. But we can replace L1 with who? With N1, because we said the two angles are equal. All right? So that gives us the chance to solve for N1. Plus 130 degrees is equal to 180. What's the reason? Angle sum in triangle, or sum of angles in a triangle, or interior angles of a triangle. Then we can solve. Transpose the 130, 180 minus 30 gives us 50. Divide both sides by 2. We get angle N1 is 25 degrees. Guys, there's no other answer. It's 25 degrees. All right. If another learner would have said angle N1 is equal to angle L1, angles opposite equal sides, then went directly and said angle N1 is equal to 25 degrees, reason, sum of angles in a triangle, that would have also been 100% correct. Okay. What I'm saying is, guys, some people do the mental maths, okay, and the addition and the subtraction in their heads. That's fine. We award them the marks. If someone would have said angle N1 is equal to angle L1, angles opposite equal side, and then went direct and said angle N1 is equal to 25 degrees, reason, sum of angles in triangle, we give the marks. We give the marks without necessarily writing out these steps. If you say angle N1 is equal to 25 degrees, because you can clearly see that what two equal angles added together with 130 will give me 180. You can do that mentally in your head. And angle N1 is equal to 25 degrees, sum of angles in a triangle. Do you know what, guys? I would award full marks. As much as I would award full marks. More work done, less work done. 100% correct, 100% correct. Not a problem. Okay, any questions? Grade 11s, you must be able to unpack this one by one, layer after layer. Euclidean geometry is weak. Young Grootman, it's not that I make you understand easily. It's just that this thing is weak. Euclidean geometry is weak, whack. So if people are crying, paper 2 and saying, Euclidean geometry is the one, it's making us cry. You are crying because you choose to stay crying. All right, anyways, let's continue. So every time I get information, guys, the minute I calculate O2, I take my pencil, I draw in there and I write the angle. 260 degrees. I get M1 plus M2, I write the angle there inside. 130 degrees. I get N1, I write the angle 25 degrees in pencil, and then I also write there for L1 as well 25 degrees, so that that information can assist me later. You see, I move on to my next question. I can see my diagram is filled up with information, and so when I come to 10.2.4, it shouldn't give me that much problems. If it does, I am the problem. You see? If it does, I am the problem. So guys, tell me immediately, what is the value of angle K? I filled in information. I have 260 degrees. Primrose, are you priming there? Are you priming there? Can you tell me? I have 260 there. I have 25 degrees there. I also wrote 25 degrees there because I know it's there. I wrote 130 degrees there. My diagram is priming with prims. So I want to know what K is. Primrose, is the rose priming there or what's happening? You have muted yourself there. Angle K, what's K? Giving reason. Yeah, Omio, you must clock it, my leader. It's clockable, this paper. It's clockable. Aye, it's clockable. Aye, it's clockable, guys. It's clockable. Paper 2, okay. Clockable. So Primrose, you said the answer is 50 degrees. Why? Primrose, I see your 50. I want to know why. I'm putting too much pressure on Primrose. Anyone, guys, who wants to give us a shot? No? Okay. Give this a shot. Me, I can see the answer already. I can see it. You see K, I can see the relationship. So now there's another theorem. So there are other theorems I need to be remembering. In your head, these theorems should just come in, you know. It's like they should fly through. It's like they are here because you've engraved them in your head. You've spent enough time individually with each theorem so that when the time of remembrance comes, it comes easily, you know. We tend to remember those things we spend most time with, you know, that we tend to remember, you know. Think about the memories that you have, that you prize in your life. You prize those memories. You prize you know, memories that you've had, good memories that you've had with people that meant a lot to you. You know? So those things come easily, you know. I think let me put it down there. Okay, so no one in the comment section can help me out there. I thought someone was going to tell me the value of N1 and give me the reason immediately. So that means our theorems, guys, are not there at the forefront of our heads. Because if they were, then this problem wouldn't be difficult. Let me just show you something here, right? So this is not with regards to center theorems, okay? Okay, I see someone is speaking. Young Grootman is saying we have to find N2. And my question is it really necessary to find N2? Why are you saying N2? Okay. We will have to find N2. Lou says 25 degrees. Lou, you need to tell me why. Why is it 25 degrees? Give me a reason and I will gladly say amen. K is 25 degrees. Primrose was saying sum of triangles. Which sum of triangles are you adding here? I need to understand that. Which sum of triangles are you adding? Lou, I love you. Lou, I love you. All right. Yeah. So Lou has the shortcut to heaven. Primrose, I see you said sum of triangles. All right. And I'm guessing you took the very long route to the answer. But Lou took the shortcut to heaven. Shortcut. Short as can be. Yeah. So you are correct, Lou. The bow tie. MNLK. The bow tie. But it's not the bow tie that has the center at the circumference. It's the bow tie that basically has all 4 points at the circumference of the circle. M, N, K, L are all points at the circumference. O is the center, K, L, M, N are points on the circumference. We would say that K, L, M, N, we would say they are concyclic. And that means quad, cyclic quad. K, L, M, N, the bow tie that has 1, 2, 3, 4 vertices at the circumference of the circle. That sort of bow tie, we know that N1 will be equal to angle K. N1 will be equal to angle K. Angle N1 will be equal to angle K. Angles in the same segment. Okay, or we could say chord subtends equal angles. ML subtends the angle N1. ML also subtends the angle K at the circumference. So hence we call it angles in the same segment. Remember, ML is a chord, right? This bottom part, right? This bottom area is called a segment, but it's a minor segment. This chord also gives us this major segment. The major segment has these 2 angles, N1 and K. We say these are angles in the same segment, right? Very important. So I love it. I love it. I love it. The bow tie with all points at the circumference of the circle. Young Grootman, okay? The acceptable reason document gives allowance for chord subtends, okay? Chord subtends, all right? So please, young Grootman, please check out the acceptable reason document, okay? The acceptable reason document is a beautiful guide, so it gives allowance for that, okay? So we can either say angles in the same segment, and when we write that, we just simply say angle N1 is equal to angle K, which is equal to 25 degrees. Reason, angles in same. It even says in same seg. Okay. Yeah, it will be posted there on my YouTube channel, don't worry. Angles in same seg. That's how we write the reason. Or it says chord subtends equal angles. Chord subtends equal angles. I mean, you could write that one too, okay? Chord so and so. You need to state the chord though. So you could say chord ML subtend equal angles. So that's another way of writing it. I think the acceptable reason document gives allowance for those 2 acceptable reasons. Yeah. So I hope we are good. Guys, those were marks that were really straightforward, I think, and I hope. Okay, so me doing this is just sort of like me making you realize that you need to know your theorems. Okay, so obviously that one has to do with our cyclic quad theorems. Okay, so now I'm going to add to my buffet of theorems. Okay, angle at the center is equal to 2 times angle at the circumference. We saw those 3 scenarios of that theorem. But our cyclic quad theorems, there's the one that says, which is this one that I just spoke about, you have your bow tie. The bow tie has all 4 vertices at the circumference of the circle. It's different, guys, from angle at the center, where you have 3 vertices at the circumference and 1 at the center. This bow tie for angle at the center is equal to 2 times angle at the circumference, and this bow tie, which is for angles in same seg, in other words, segment. Remember, it means this angle is equal to that one, or you can say this angle is equal to that one. These ones are equal in the same way. These angles are equal in the same way. That's the bow tie with all vertices of the vertices at the circumference of the circle. This bow tie stands for angles in the same seg. The theorem says an arc subtends equal angles at the circumference. So this arc subtends that angle at the circumference and that angle. So these 2 angles are equal. This arc subtends this angle at the circumference. It also subtends that angle at the circumference. So we say these 2 are also equal. Okay, guys, the theorems, if you know them, you are fine. Okay, then for the quad theorems, we also have this one, of course. This one has to do with the opposite angles of a cyclic quad are supplementary. Okay, opposite angles of cyclic quad. We say the opposite angles of a cyclic quad are supplementary. Okay, in other words, the opposite angles of a cyclic quad will add up to 180 degrees. Okay, that's a cyclic quad theorem. Then we have this one, which I'm sure you guys all know. This one has to do with the exterior angle of a cyclic quad is equal to the interior opposite angle. So we usually say x angle of cyclic quad. X meaning exterior, angle, right? And then of cyclic, then quad. So that's basically whenever we identify 2 angles in a cyclic quad where the exterior, remember the exterior is always the angle that is in line with the side of the triangle. It is an exterior because it's in line with the side. It is an extension. It is produced from a side of that quadrilateral that is internal to your circle, the exterior angle of cyclic quad. So we say that angle is equal to that one. Guys, these are our cyclic quad theorems, and we need to know, how to apply. Now, imagine if you don't know these things, guys. I mean, really and truly, you're going to look at diagrams and never figure out anything. You're just going to look at these diagrams and you're going to be like, hey, this diagram, too many lines. Why are they complicating my life? Why am I even doing maths? Such a pain, Yeah. But if you know your theorems, if you know your diagrams, you'll be fine. Then underneath your cyclic quad theorems, we have what we call corollaries. Corollaries. All right. These are deductions that have come due to angles in the same segment. Corollary number 1 says, if you have 2 chords, they are equal, guys. If you have equal chords, these equal chords will subtend equal angles at the circumference. So we say equal chords, equal angles. Equal chords, equal angles. All right. This is not a theorem. It is a corollary. It has been deduced from angles in the same segment. So the first corollary of angles in the same segment is equal chords, equal angles. So whenever you have in a circle, you have two chords, and you can clearly see that those two chords, they are equal and they are subtending angles at the circumference, then rest assured those angles that are subtended by those equal chords are actually equal. The angles are also equal. And this is the reason. Equal chords, equal angles. The other corollary that comes from this theorem is this one. And don't mistake this theorem with vertically opposite angles. It's not. It's not vertically opposite angles, guys. Okay. So if we have equal chords, these equal chords will subtend equal angles at the center. Hey, guys. We also say when we are using this reason, equal chords, equal angles. We don't even have to say more, because the reason here and the reason there, we write the same reason statement, but of course, when we write the reason for this scenario, we are referring to a chord that is equal to another, subtending equal angles at the center. So that's when we use this guy here. Whereas here, we use this one whenever we are talking about equal chords subtending equal angles at the circumference. Remember, circumference is the edges of the circle, whereas the center is the central point of our circle. It's basically where the diameter will also pass through. It is where the radius comes from to the circumference, and it is a very important point of the entire circle. All right. So this is equal chords, equal angles. Please, guys, the chords need to be equal in order for the angles at the center to also be equal. Then the last one has to do with equal circles. The minute you have two circles that are equal, so this one says equal circles, equal chords, equal angles. It's like three-part. It's three-part, this one. Equal circles, equal chords, equal angles. It's three-part, right? So here's the scenario that you can actually think about here specifically. Okay. So let's just say you have equal circles. These two circles, they are, in other words, the circles are identical, literally, all right? And then you find that within those circles, you have chords as well that are equal, right? So it's almost as if these two triangles are also identical. So you have identical circles, okay? For two separate circles, of course, you have two identical diagrams within those circles, respectively, and each one has chords that are equal. So that means the angle that will be subtended at the circumference by each chord will also be what? Equal. I repeat, you have two circles, they are the same, they are equal, in other words. All right, they have the same identical diagram within them, like you would say a triangle, respectively, with chords, obviously, that are equal. And obviously, each equal chord will subtend the same angle for each equal circle at the circumference of each respective circle. So that's why we then, whenever we are using this particular diagram, we can say equal circles. So we add a new part to this one, to these two, by actually saying equal circles. Then we follow it up with what we had already been saying, that is equal chords, because you can see, guys, that these chords are equal. And then lastly, we say equal angles, because the angles will also be what? That are subtended at the circumference. They'll be equal. Respectively, the angles will be equal. So equal circles, equal chords, equal angles. These guys are also very important. Now, if you don't know these, hey, you don't know angles in the same segment. You don't know opposite angles of a cyclic quad. You don't know exterior angle is equal to the interior opposite angle. You don't know equal chords subtend equal angles at the circumference. You don't know equal chords subtend equal angles at the center. You don't know that equal circles, if you have them, that have identical triangles, in other words, each respective triangle will have a chord that is equal. Those equal circles that have equal chords actually subtend as well equal angles at the circumference. If you don't know these things, guys, you don't have this knowledge. How in the world do you expect to have some sort of light come on when you are doing geometry problems? That is my question to you. That is my question to you guys. Like, what are you expecting? Miracles won't happen if you don't have the knowledge. Okay, and people perish. Why? Because they lack knowledge. That's why people are perishing. That's why learners are not doing the things in geometry. It's because they lack the knowledge. So you must have this basic foundational knowledge. And I always suggest to grade 11s that when you are learning geometry and you first get exposed to all these theorems, you must have a page, like a formal page, guys. A formal page. It's the Christian church. Yes. This is like geometry church. If you are starting, if you want to develop your geometric eye, you must actually write down, draw all these diagrams with all of them with their respective acceptable reason. Underneath each diagram, write the acceptable reason. Underneath each diagram, write the acceptable reason. Underneath each diagram, write the acceptable reason. Group the theorems. Okay, so group the theorems. The center theorems all together. The cyclic quad theorems all together. Okay. Additionally, guys, we have the tangent theorems. And guys, I'm not looking at something as I am doing this. It's literally, this is all coming from the head, because these are things that I hear now. They've stuck with me. They are there. There's the tangent theorems. All the tangent theorems, you must know them. Okay. Can someone give me the tangent theorems that they know? Just off the top of your head, one that's coming to mind, where there's a tangent in it. A tangent theorem, just in the comment section. Tan chord, tan perpendicular to red. Now, when you think of tan chord, hopefully, you can see this. Okay. You must see it upside down, and you must see it the right side up as well. Right? So now you are thinking about, there must be this tangent. No? Because the tangent touches one point at the circumference. There is a triangle. All vertices are at the circumference. They must be at the circumference, all vertices. Okay. Then what does the tan chord theorem say? The tangent chord theorem. Okay. The acceptable reason, they say tan chord theorem. The entire thing, actually, in the acceptable reason document, when you write the shortened version, it says tan chord theorem. Okay, it's not shortened in the least bit. So you have a tangent, the angle formed by the what? By the tangent and the chord. The angle formed by the tangent and the chord is equal to the angle subtended by the chord. This chord here subtends this angle. So the angle formed by the tangent and the chord is equal to the angle subtended by the same chord. So it's not only this angle that's there, there's this one as well. So I'm just going to put double strokes for this one. Because please, guys, don't think that this angle and this one, they are equal. No, they are not. These two angles are not equal. right? It's this angle and that one that are equal, given that all vertices are at the circumference. Very important as well that all three vertices must be at the circumference. The corners must be at the circumference. So this angle here is equal to that one. Are you with me? The angle formed by the tangent and the chord, the angle formed is equal to the angle subtended by the same chord. So this side as well, it means the angle formed by the tangent and the chord is equal to the angle subtended by which one? By this chord. This chord subtends that angle. So these two are equal. These two are equal for this reason. Tan chord theorem. That is the tan chord theorem. The angle in the alternate segment, they usually use that word as well. The angle in the alternate segment, the angle subtended by the chord. Guys, I suga matota. Okay, tan chord theorem. Okay, then people said tangent perpendicular to red. Radius, tangent. Okay, sorry guys, please forgive me for my skewy line. This should be a straight line touching just that one single point at the circumference. What are we saying here? We are saying this tangent is going to be what? Perpendicular. Tan perpendicular to red. Okay, so this angle is 90, guys. Okay, it's not like the angle 90 is given to you. No, whenever there is a situation where you have a tangent, okay, remember the radius can be extended to the other side of the circumference. It becomes a diameter. Still, diameter is perpendicular to the tangent. Okay, please guys, tangent perpendicular to diameter. Part of the diameter is a radius. So you can use tangent perpendicular to red for everything. Doesn't matter. Even if it's a diameter, you can say tangent perpendicular to a what? To a red. Why? Because the radius is part of the diameter. You see? Then the last tangent theorem that you should know. I didn't see it in the comment section. I'm waiting for someone to type it. Thank you, Shimmy Shimmy. Shimmy Shimmy. Shimmy Shimmy. Shimmy Shimmy. Pikachu. Yeah, Shimmy Shimmy is Pikachu. I can see there. Eh? Pikachu. Here we are, bro. There we go. There we go. Okay. Pika, pika. There we go. Pika, pika. Okay. Tangent, tangent. Tangent from the same, which is the same point. This is the same point they are talking about. Okay. The tangent, tangent 1, tangent 2, tangent 1 and tangent 2 from the same point. Are you with me, guys? Guys, I don't know what more you want from me. So what are we saying about tangents from the same point? They are equal. Tangents from the same point are equal. That's what we're saying about them. Okay? They are equal. They are equal. Okay? Tans from same point, or we can say tans from common point. Okay? This is the short reason. Tans from same point, or we can say tans from common point. Hi guys, they are equal. They are equal. They are equal. Tangents from the same point, they are equal. All right. Pika pika. I hope you guys really get it. Pika 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 pika. Tan chord theorem. Tangent perpendicular to radius. Tangents from the same point. Hi, they are equal. They are equal, guys. They are equal. The equal sign is never given to you. You just see tangents from the same point. When you know the conclusion is that they are equal. The perpendicular, the right angle is never given to you. But if you know if there's a radius and there's a tangent, you know that the angle 90, you know that. Tangent a tangent chord theorem. A chord, yes, and a tangent. An angle formed. The angle equal to the angle subtended by the same chord. This guy equal to that guy. Tangent, chord, angle formed. Chord subtends angle at the circumference. Angle equal to this one. Tangent chord theorem. Hi guys, what more do you want from me? Tangent theorems. You see? So if our tangent theorems, so all of these must go up. Guys, do the whole colors and stuff. Take these diagrams, put them up. You know paper 2 is going to harass you if you don't know these guys. Take them, put them up. Right? This is Zinxumalo. You must know her. You must know her music. You must know the sings. Kala, 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 kala. You see, if you don't know her pain, you won't be able to identify Zinxumalo. You don't know nothing about her. Yeah. Yeah. Shepet. Yeah. That's him. Tyler. Tyler. Tyler is there. Tyler is there. Put him up. Put her up. Put up her poster. Take Tyler down. Put the real Tyler up. Tangents from the same point. Tyler needs to be up there. Put angle at the center, 2 times angle at the center. Put them up. Scots Mapuma, yes, put them up. Put the Scots up there. Scots Mapuma there. All right? Yeah, put them. This one, your cyclic quad theorems, put them up. All of them, all these guys, favorite artists, take down, put up. You need that info, right? And then when you have that diagram, whenever you do Euclidean geometry, when you are practicing for yourself, you simply take this paper, you put it next to you, and then when you are doing Euclidean geometry, you always go back. If you are looking at the diagram and you seem to be lost as to what needs to be done, go and refer back to these diagrams and see if something won't click. The more you use these things, the more you train your geometric eye, the more you spend time doing these, you're going to see, guys, surely something is going to click, something is going to be better than it was in the past. Rather than look at the question, just skip the entire thing and not do or attempt or get any marks. All right. I really appreciated a comment. Someone actually sent me a message, inbox message a few days ago, and said to me they really appreciate it because I once did a live lesson on Euclidean geometry. I actually did a series of lessons on Euclidean geometry for grade 11 during term 2, and I posted up the lessons that I did. They were very interactive, the lessons. I posted them up on my YouTube channel. So the learners that were there, they said even then that they benefited a lot because we unpacked every single one of those there. I did a theorem a day. Like I did one theorem a day, and we looked at problems pertaining to each specific theorem. So the learners there at that time were like, yo, this is really helpful. We're beginning to see what we need to see. And I was like, oh, that's great. That's awesome. And 2 days ago, I got a message from one particular learner whom I didn't even know was joining my live lessons. And she was like, sir, thank you so much for the geometry lessons that you did during term 2, because for my geometry part of paper 2, I got full marks, and it was thanks to the assistance and help of joining the live lessons and actually going through the theorems one by one. So I was really, really happy about that, because at the end of the day, it must impact, your personal performance when it comes to paper 2. If it doesn't, hey, matata fail. Okay, so I did the tangent theorems. Who else is missing? I think in the center theorems we are missing these 2 guys. We are missing this guy, this one, from our center. There's this guy. Let's start with this one. And then there's this one. You see this one, based on the information given, all right? Yeah. Me, I'm not so much gung-ho or preoccupied with whether it's theorem 1 or theorem 2 or theorem 3, because in the exam, you will never be asked the theorem number, but you must know the particular theorem, what it says, what is the statement of the theorem. The line drawn from the center, because you see, the thing is, sometimes they give you the statement and they say the line drawn from there, and then they leave a line, and then you need to fill in the missing word. So you must know the theorem statements. You must know what they say. So this one says a line drawn from the center of the circle, line drawn from the center to the midpoint of a chord, line drawn from center to the midpoint of the chord. Why is Sir knowing that it's line drawn from center to the midpoint of the chord? The thing is, I'm looking at the diagram and I can see they've made these markings, which means this point is the midpoint. So line drawn from center to the midpoint of the chord. What about it? Well, I'll tell you. The line drawn from center to the midpoint of the chord, this is a chord, all right? A line from one end of the circumference to the other is a chord. So a line drawn from the center to the midpoint of the chord, what does it do? It is perpendicular to the chord. In other words, we can say OB is perpendicular to AC. Straightforward like that, guys. OB is perpendicular to AC, which means that is a right angle, that is a right angle. So we can say OB is perpendicular to AC. And the reason for that, guys, is simply this: line from center to midpoint of chord. And that is simply that. The reason is in the diagram. The statement is unseen. It's something we don't see in the diagram. The fact that we said OB is perpendicular to AC is based on something that we see in the diagram. What do we see? A line from the center to the midpoint of the chord. So then what we're writing down is something that we don't see. So we're exercising a lot of faith, if you ask me. And those people that are saying, faith is none. Hi guys, we are exercising a lot of faith even in maths. Are you kidding me? We're writing something that is unseen. We don't see OBB perpendicular to AC, but we're writing this thing based on something that we see. Something that you can't see from the diagram, but we're writing based on something that we do. Suka, come on guys, Suka. OB is perpendicular to AC, line from center to midpoint of chord. That's what would be your statement and reason. This one, what does it say? A line from the center perpendicular to the chord. Esther Christie. Yeah, you can sense it Sunday today, guys. Jesus and faith. They have to feature, man. Have to feature. That is the basis of why this channel wouldn't be here if it wasn't for them. So I can't not articulate that. You see? So the line from the center perpendicular to the chord. Line from center perpendicular to the chord. What does it do? What it does is something I don't see in the diagram. It's something that I will write as my statement. I don't see it, but it's based on something that I see. Yeah, just like my faith in the Bible, a faith in God is based on something that I see, which is the Bible. The Bible is there. It's a physical written record. I can read it, and from there I can be able to develop faith in the unseen. Make sense? So even here, look at this. O, B, A, C. So what this guy is saying now, we can conclude and say AB is equal to BC. Hi-bo. How come? AB is equal to BC. Yes, AB is equal to BC. Why? Line from center perpendicular to chord. That is our acceptable reason from the acceptable reason document. Not made up, from the document. I subscribe to the document. If I'm writing my reasons, I'm not freestyling the reasons. I'm writing as per what is in the biblical word of the acceptable reason document. I state the reason as per what I see there. All right. I don't want to deviate. I don't want to add or take away from what is in the document, I write according to that. So that even when Mr. Marker in the marking center, when I'm in grade 12, comes along and wants to say, I don't agree with what this man is saying. If he consults the word, the text, the acceptable reason document, they will see that this guy is aligned. You see? So I have no choice. I'm aligned, my lead. I'm aligned. AB is equal to BC, line from center perpendicular to chord. I hope we get the point, guys. Hope we get the point. All right. So those are my center theorems. In addition to these center theorems, together with this one that I nearly forgot. Which other center theorem, guys, is very key that I've forgotten? You will remind me now. It's not that I've forgotten, but I choose to forget. You tell me, what other center theorem have we forgotten that we need to put in there, which is very key as well? Come on. I know my people, you know your stuff. The one remaining center theorem that I did not write down, which needs to be written. Which one? Come on. Angle at the center has been taken care of. We are sorted. Line from center perpendicular to the chord has been taken care of. Line from center to the midpoint of chord taken care of. Star Christy, you're a star. 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 Okay, so yes. Star Christy is the star that has given us. Yes, Star Christy is a star indeed. So there we have it. Diameter. What about this guy? Diameter does what? Thank you, Zianda. Thank you so much. So Star Christy, thank you so much, Zianda. Very, very worthwhile comment there. Really appreciate it. It touches my heart. Big time. Yes, Lou. I agree. Angles in a semi-circle. And yes, Omio, diameter will subtend 90 degrees at the circumference. Diameter subtends 90 degrees at the circumference. Okay. Yes, guys. So the diameter of a circle subtends 90 degrees at the circumference. If you think about this a bit more closely, this diameter, it's like this is an arc, right? The arc subtends the angle here. This angle is 180. But remember, the angle at the center is 2 times the angle at the circumference. So if this is 180, this must be 90. So it makes sense this diameter subtends 90 degrees if we look at it in light of angles at the center being 2 times the angle at the circumference. Because the arc subtends 180, so indeed the same arc subtends an angle at the circumference. So therefore, if this is 180, it is 2 times the angle at the circumference. That must be 90. The logic behind it is that. But of course, whenever we utilize the fact that that angle is 90, we just simply say, oh, the diameter subtends 90 degrees. We can simply say angles in a semicircle. So that's another center theorem that we need to know very well. Guys, so many artists to know. Michael Jackson, resurrected from the dead. Michael Jackson, Scott, Tyler, all these beautiful artists that we love and know. Beyonce, I see her daughter is also coming into the fray. All these people. I know these artists that you guys love. Lindo, all of them. Amanda Black. By the way, guys, Amanda Black is someone that I knew from varsity. That's another interesting thing about me. Billie Eilish. Yes, Billie. Yeah, Billie Eilish, Let's not forget Coldplay. Let's not forget Coldplay, guys. Coldplay did a bust in their recent concert. I'm sure you saw the popular video that's been going abuzz with the CEO. I dare not say J. Cole. Hi guys, all these people need to know them. J. Cole, right? So our cyclic quad theorems, please guys, we need to know them. Center theorems, we saw them, all of them. Center theorems, all the center related theorems. Tangent theorems, all of them, all of them, all of them. Okay. Yes, indeed you can. Zianda, you can. You're more than welcome to share the live. Yeah, you can share the live. You can share the live. You can share the live. Yeah, I mean it's okay. Yeah, even though I'm sure I'm probably going to be leaving it very soon. But my grade 11s, please do me a favor. We do want to get better in our geometry, right? And we want to not just become better, but we want to be significantly amazing. So if we do grade 11s, grade 12s, let's make sure that we get our theorems and our reasons and our diagrams sorted out in our heads. What does the diagram say? You know, we need to sort that out in the head. When we sort these things out in our heads, then we will be in the position of being able to answer the questions easily. No problems, right? I want to check out here if we can't look at a... Yeah, you see, this is what I was meaning, right? So for the beloved grade 12s, no, definitely, Star Christie. That's kind of one of the intended reasons why. Okay, so this is a 2000, and I mean this would be applicable to the grade 12s. But look, because grade 12 encompasses the grade 11, yeah, the grade 11 content. Look at this, guys. Look at this. All right, this one will have direct reference to what grade 11s are currently busy with at school, or what they should have started with beginning of the week last week. This has to do with triangles, right? Triangles, solutions of triangles, your area rule, sine rule, cosine rule. This has to do with that. But you can see that they have integrated topics here. There's an integration of topics here. Can you see the integration of topics? Hey, guys, they've intermingled trigonometry with geometry. It's like, to become one thing. Because here you have sides given to you, AD and DC, then 100 degrees, the angle. Then there you have an angle here, which is 40 degrees. And they are asking you to calculate the following correct to one decimal place, the length of who? Of BC. Right? And there is a method and a way in which we can unpack and unravel these questions when we answer them, which makes life very nice. Yeah, so yes, I love Calvin. You are amazing there. Two sides and an included angle. Sus. You are sus, right? I usually call that SAS. The side angle side angle side. You know how people nowadays are like saying, you are so sus, you are sus that. Me, I take all of that and I incorporate it into the maths. So now we're talking about SAS as it relates, obviously, sometimes maybe to congruency of triangles, but specifically here, one of the cases or one of the scenarios that allows us to use which rule? Sine rule, cosine rule, area rule. Which rule allows us to use angle and included angle and two sides, which is SAS. I usually say it's SAS. For my learners, just for them to remember, it's SAS. Omeo, it's not the sine rule. Okay, sine rule, it does not, we can't use the sine rule in this scenario because we have an included angle and two sides. Remember, if you were to use the sine rule in this triangle, look at this. You have this angle, you have two sides. This side is opposite that angle. Unfortunately, we don't have an angle here. This side is opposite this angle. We don't have an angle there. And given the triangle we have here, we can't even find these two angles. So that's why we can't use the sine rule. The sine rule is unusable in this situation. So you should be able to rule it out. But you need to first understand from the get-go what are the conditions that allow us to use the sine rule and what are the conditions that allow us to use the cos rule. The sine rule is utilized when we have a given side with its opposite angle or a given angle with its opposite side. Then maybe we need another angle with a side that is missing, or we need another side with an angle that is missing. Then you can use the sine rule, because remember the sine rule has to do with the side with its opposite angle. That's very important. But cosine rule, two scenarios to use the cosine rule. If you need a missing side, you need sus to be intact, side angle side. You can use sus to find the missing side. Or the second situation is SSS. In other words, we have to have a side, side, side for your triangle. And in that situation, it's when you are looking for a missing angle. So please, guys, know the conditions of use for the rules. If you don't know the conditions of use for the rules, these problems become painstaking and a exercise of loss of marks unnecessarily. So please, guys, there are rules, or let me say, there are conditions of use with many things in mathematics. If you don't know the conditions, that's where things go south. All right. That's why you need to spend a reasonable amount of your time trying to understand the concept and then paste it up on the wall. Paste it up on the wall. Paste it somewhere where you can see it. Take down these Billy-ish people and put up the relevant information. You need it for this year. Grade 11, some of you are wanting to ensure that you have sweet marks for the end of the year so that you can apply nicely next year. So please, guys, dedicate the time. It's worth it. If you're in grade 12 already, you don't have time. Okay? Yeah, please, guys, I beg of you, you must give off your time, right? Billy-ish, yes. The length of BC. Okay, so the length of BC, right? We'd have to first find AC, of course. Once we have IC and we have IC convincingly, then we can, utilize our knowledge of quadrilaterals, because this is a cyclic quad. We do have 100. We can find angle B. You know what I'm saying? Because these are opposite angles. So with the minute you find side IC, which you'll have found using the cosine rule, you'll then be able to use this side that you have found, and then the angle which you'll have found using opposite angles of a cyclic quad. Remember from geometry, cyclic quad. So if this is angle D100, this will be 80 degrees. You will have a given side and an angle. Then you will have an angle with a missing side that you are wanting to find. So sine rule can be used. You see the conditions of use. So you see now, guys, that even in this question, these people in this exam, they want us to incorporate our Euclidean geometry knowledge. Now, the Euclidean geometry knowledge is not there. Then what? Kill a whale. You see, then we kill ourselves because, so please, guys, Euclidean geometry, you must know. All right. And even when I approach these kinds of questions, something I love going through whenever I'm doing questions that have to do with solutions of triangles. Please, guys, here they're saying the length of BC. So what you do is you say, where is BC? Where is BC? So you go there. Here is BC. In which triangle is BC? BC is in triangle ACB. Do I have enough information in triangle ABC to use a rule to find BC, or to probably use my trigonometric definitions? Now the thing is, I don't have enough information. So that means triangle ABC, I need to leave that triangle for now until further notice, grade 11. You see, Yeah, and even grade 12, because this is a grade 12 paper, but there's grade 11 concepts, grade 11 theory that is fundamentally being tested here, but at grade 12 level, grade 12 paper. Are you with me? So this is grade 11 in a grade 12 paper. So if you are in grade 11, you are in a good place. You are in the right place. And it's very key, this thing. So let's go back. What did I say to you? Length of BC. First question you ask, where is BC? There is BC. Which triangle is BC in? BC is in triangle ABC. Do I have enough information in that triangle to use either a rule or a trig definition? No, I don't. So that means for now, I say goodbye to BC, but I note the fact that BC is opposite an angle that I've been given. Which means in the future, when I do find BC, there will be something that will have to do with this side and the angle that I'm given. And that's giving sine rule vibes, if you know what I mean. But anyways, I leave it to rest for now, and I go to the triangle that is next door to triangle ABC, which is triangle ADC. I go and ask the same question. What will connect me back to triangle ACB is if I find side AC. So if I look at triangle ADC, what do I have? A side, an angle. Sus. Sus means what condition am I meeting and which rule can I use? Well, if I look first and foremost, what type of triangle is triangle ADC? Is it a right angle triangle or is it a non-right angle triangle? These are things you need to establish as well. A non-right angle triangle will use the rules to find sides and angles. But a right angled triangle will use the definitions to find missing sides and angles. And by that I mean the trig definitions. SOHCAHTOA, sine opposite over hypotenuse, cos adjacent over hypotenuse, tan opposite over adjacent. So this is a non-right angled triangle. It's a non-right angled triangle. It is not right angled. So as a non-right angled triangle, I will go ahead and use the what? The rules. Sine rule, area rule, or cosine rule. Which rule will apply for me to find AC? Which rule will apply? I can use the cosine rule for SAS, S-A-S. So I punch this in, use the cosine rule, guys. That means I will say AC squared is equal to AD squared plus DC squared, right? Minus 2AD times DC cos angle D. And then I just substitute all those values in that place and get my AC. Yes, Star Christy, because it has D, which is 100. There is no ways in heaven or in hell that triangle ADC would be right angled. Do you know why? Because if this angle is already 100, imagine if this is 90. What's 100 plus 90? It's 190. Already this triangle can't be a triangle that satisfies the conditions of the sum of angles in a triangle. So that's why I say this is non-right angled. It's a non-right angled triangle, this one. Are you with me? Hey, and these things are very important. These things that I'm saying, they are very key for unlocking knowledge. So the minute you find AC, you are a step closer to success because you have AC, right? Then, what else can you find? You can find angle B. Based on what? Well, this is a circle, and you've been told that ABCD is a cyclic quadrilateral. So if it's a cyclic quadrilateral, what do you know about angle D and angle B? These are opposite angles. So if they are opposite angles in a cyclic quad, what do we know about the opposite angles of a cyclic quad? We know that angle B will be 80 degrees because the sum of the two angles should be 180. In other words, they are supplementary. Then, bam, you have an angle. Bam, you have a side. Bam, a side and an angle opposite each other. So, yay, we are one step closer. Now we are back to triangle ACB. We've left triangle ADC. We are back to triangle ACB. Now we have a side, we have an angle, which is angle B. So a side with its opposite angle, and then an angle with a side that we are looking for, which is BC. Sine rule in the bag, sine rule. So we just say BC over sine 40 is equal to AC over sine of 80 degrees. Bam, solve in the bag. Boom, booyaka. All right. No pain, no gain. No pain, no gain. All right. So easy 6 marks, this one. All right. You guys will do the calculations. You can have fun with it. I mean, really and truly, me, I am just here to sort of like help us to get our minds thinking. Okay. So you need to, when you see a question, if they say the length of BC, where is BC here? What type of triangle is BC? Non-right angled. Is there enough information to be able to find BC? No. So that means goodbye for now. I'll come back later. Let's see if we can't utilize this triangle, transfer info this side, and then find stuff. Well, let's go. We go to triangle ADC. We can find AC, which relates back to my triangle ABC, using the information in triangle ADC. When we look at the info, side, angle, sus, cosine rule. We substitute find AC. We get AC using the cosine rule. We get angle B using the knowledge we have of angles opposite each other in a quadrilateral, cyclic quad, sorry. We get B, and then after that, we use the sine rule because we have this angle, B, we have this side, which is opposite the angle, and then we have a side, an angle with a side that is missing. So sine rule can be used, and we can get that. Lastly, 7.2, the area of triangle ABC. You will have BC, you will have this angle, you will have this as well, side. Now, with the area rule, we also need a situation of sus in order to be able to use the area rule. The area rule can only be used in a situation of sus, SAS. Hey, this guy is becoming famous. So sus is used in the cosine rule to find a side. Sus is also used in the area rule to find the area. Sus is doing the things, my leaders. Sus is doing the thing. Side, angle, side, meaning the angle included between two sides. Very important. So remember, guys, I will have AC because I did find it when I was trying to find BC. I will have BC because I will have found it by this time. So that means I will have two sides, this side and that side. All I need is this included angle. Because remember, if I have this side and I have that side, I just need this included angle. And I'm sure I can find that included angle because if that is 40, that is 80, in this triangle, the sum of angles in a triangle should give me another angle here, which should also be what? 80 plus 40, 120 plus what gives me 180. So this will become what? Oh, see here? Tell me before I die. Tell me. Yes, it will add up to 180, but I'm wanting specifically now the angle. Angle C, in fact, angle ACB will be equal to, thank you, Homo, so it will be 60 degrees. Okay, so with those two sides having been found, I'll be able to use the area rule. Because the area rule, guys, is simply that. It's the product. Okay, so for instance, if you have ACB, you have that angle, you have this side and this side. All you simply do with the area rule is say area of triangle ABC is equal to half. Now, half what? The product of the two, 1, 2. Which two sides? The two sides. AC times BC times what? Sine of the included angle. So I would say sine of angle ACB. And that's it. You plug into the calculator and remember at the end, your answer must be in unit squared. Please don't forget that part because this is area that we are talking about. We don't have any units that have been given like centers or millimeters. So obviously, since the units we've been given, it's like 10 units and so forth, then our final answer, we are writing it in the same given units. But then since it's area, remember area is measured in square units. Ne? Akiri, guys. All right. Okay, so this would be obviously something that for the grade 11s, for instance, this is a nice question because it integrates two important fundamental topics. Okay, it integrates both Euclidean geometry and it actually merges Euclidean geometry together with, you see? So together they just flow nicely. All right. Where am I taking this? This is coming from a past paper, Northwest. This is a September trial paper for grade 12s, but it's a grade 11 question in a grade 12 paper. So, and then you think that grade 12 to grade 11, they are they are not mutually exclusive, guys. Grade 11 and grade 12, they are not mutually exclusive. They are not mutually exclusive. If you are a learner who knows probability well, you will understand what I'm saying when I say grade 11 and 12 are not mutually exclusive. They are not mutually exclusive, those two. You get me, ne? They are mutually inclusive. Very good, Natalie. I love you. Love the lingo there. You see, if you understand the maths is really helping us a lot here. It's giving us terminology, things to say, and all of that stuff. So please, guys, don't make high marks in maths become an asymptote. Are you with me? Don't make high marks in maths become an asymptote. High marks in maths should not become an asymptote. I hope you are getting me there. Yeah, if you don't get it, forget about it. Okay. I just wanted to sort of like, don't make high marks an asymptote. High marks in maths should become the word from the beginning, All right. Look at this one. Look at this. Complete the following statements. Look, let's see now if people know statements from geometric statements. You guys, you see? And you think trial papers, they will just, because some of you, I know you're like, the paper 2, geometry from grade 12. Hey guys, you don't, please remind yourself of this thing. You must remind, okay? The geometry statements from grade 11, don't forget them, guys, please. There, the following statement number 1. The angle subtended at the circle by a diameter is, the angle subtended at the circle by a diameter. The angle subtended by a diameter is what? Hey, these people, I'm listening, guys. I'm waiting for you to speak. The angle subtended at a circle by a diameter is. 1 mark? Are you telling me the 1 mark is just going to go begging? It's going to be lost. The angle subtended at the circle. The angle subtended at the circle by a diameter. A diameter is, thank you, homozo, is 90. Is equal to 90 degrees, guys. Please, please, please. Equal to 90 more specifically. Calvin, thank you. Kevin, yes. Star Christy, you are a star. Omeo, that question mark must be followed by an exclamation mark. If you are still punching in question marks, it means you are in doubt. Exclamation mark means you are certain, you are sure. Please, let's write the right punctuation. Right, 8.1.2, the angle between a tangent to a circle and a chord drawn from the point of contact is equal to tell me, I'm listening. The angle between a tangent to a circle and a chord drawn from the point of contact is equal to. Sikasa, it's not equal to 90. No, Lou, no, it's not equal to 90. Lies, lies, lies. The angle between a tangent to a circle and a chord, please take note, and a chord drawn from the point of contact is equal to. Yes, Kevin, it is the tan-chord theorem, but what does it say? What is the finishing of that statement? Okay, I want to harass you with this so that you realize that I need to know my statement. I need to know my statement. If I don't, it's gonna be a pain. It's gonna be a pain. It's gonna be a very, very big pain. All right, please, guys, go, put up, raise up a banner in your room with all the statements. Okay, is equal to, Lisa Dan says, is equal to the angle subtended by the same chord. Lisa, you are amazing. You are amazing. Lisa 10, guys. Lisa 10. Lisa 10. Thank you so much, Natalia, for the rose. Really appreciate it. You're such an amazing person. Thank you. Thank you, Kosahan. Really appreciate Kosahan there. We've got a Kosahan who's a model. Thank you so much. Lisa. Hey. Yeah. Sakanya 10. Thank you so much there. Appreciate it there. So please, guys, take note of that statement. The angle between a tangent to a circle and a chord drawn from the point of contact is equal to the angle subtended by the same chord. Yeah. Or sometimes they say is equal to the angle in the alternate segment. Okay, that would also be 100% correct. The angle in the alternate segment. Right. So these are things we need to note. Right. Please, statements. Let's be about them. Let's look at 8.2. In the diagram below, ED is a diameter of the circle with center O. Ooh, this looks nice. In the diagram below, ED is a diameter. Where is ED? ED, there is ED. Okay, ED is the diameter of the circle with center O. ED is produced to C. All right, so the E and the D is produced, meaning this is in the same line, all right, because it's produced to C. It looks familiar, very nice. And CA, yeah, remember, guys, in Mpumalanga 2016, if maybe teachers are obviously like making copies, giving you common questions, we recycle questions, guys, for the purpose of exposing you to exam type questions. So if it's familiar, that's great. ED is produced to C. CA is a tangent. Where is CA? Here you are. C to the A to the C to the A. CA, some of you wanted to be chartered accountants. There is your tangent, guys. There is your tangent. CA is a tangent to the circle at B. All right. Then it says AO intersects. This word intersect, it means it cuts across, intersects at BE. Remember, the word intersect just simply means to, it's crossing, overlapping the line EB, that's all. It's not like it makes it equal, but intersect is just to cut across, all right? But if it was bisect, it would be a different story, but it's just intersect, okay? Natalia, you are awesome as well, eh? You're very awesome. Okay, so AO intersects BE, right? At what? At F. Are we together, guys? I hope we are good so far. Then lastly, we are told that BD. Ooh, big statement, this one. BD is parallel to AO. Woo! Now, guys, parallel lines have some amazing relationships that come about. Talk about parallel lines have 3 crucial critical relationships. You know, just like you have 3 relationships, or let me say you have different types of relationships. You have family relationships, you have friend relationships, and maybe you have an extra fun relationship, which I'm hoping you are putting at bay at the moment, because we can't afford to be having a bay at the moment, because you need to put it at bay, far away right now. Academic performance may be influenced, if not put at bay, by the bay, if you know what I mean. Okay, so CA is a tangent. What would we be without parallel lines? Indeed. How I wish, Calvin, you guys, male and female, would remain as parallel lines, never touching, equal gradients, equal performance, equal desire to succeed and do well, but never touching, just never meeting at all. Parallel lines, really and truly, what would we be without them? So yes, Kid Lash, you are 100% correct. The 3 relationships: alternate, corresponding, co-interior. Someone said fun there. Alternate, N or Z. Corresponding, F. Co-interior, U or C. Okay, depending on how you're looking at it. So I love that, guys. All right. Natalia, if our parents weren't parallel lines, we wouldn't be here. Yeah, sure. At some point we intersect, but it must happen at a stage in life. Please, guys, please, it must happen at a stage in life where at least there's a little bit more growth, maturity, and responsibility. Trust me, you will thank me one day. All right, so AO intersects BE at F and BD. So BD is parallel to AO. Okay, now we are told let angle E be X. So X is there. And these people, what they want from us is we must write down with reasons. This is a very nice question that they like, generally speaking. They want us to write down with reasons 3 other angles, each equal to who? To X. So look very carefully at my diagram. There is X. Okay. Now, I like whenever this is given to me as a paper, I take my diagram, I twist it around. I take my paper, I look at it from this side, that side, I look at it from this side, that side, this side, that, you know what I mean, guys? You know what I mean? I twist it around so that I can see. And whilst I'm doing that, because I'm still in practice mode, all right, preparing for the test, preparing for the exam, I have my diagram, the one that I spoke to you about, the one you need to have up in your wall. You have to have that close to you, right? So that you can actually look and see which things am I seeing in this diagram that relate to the same diagrams with the correct reasons that I would attach if I was to say a certain angle is equal to another. Does that make sense? So you use that page. It has to be there so that you can train your geometric eye and develop it. Then you'll be okay. Things will get better. Incrementally, they'll get better. It gets better, 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 better. Give your life to Christ. He'll give you paradise. You know what I mean? Okay, so there we have it. So I see someone says before Tanchord theorem. B4. Oh, guys. Oh, who is that? Kid Lash. The Lash of the kids. This guy, this guy, this guy. Are we giving Kid Lash a round of applause? B4. B4. Tangent, right? Chord. Chord. So B4, we have the triangle, remember? All 1, 2, 3 at the circumference of the circle. Chord, tangent, yes. Angle formed by the tangent and the chord. So this angle equal to the angle subtended by the chord. So 100% correct. This is x. This is x. Okay, very good. Very good, Kid Lash. Okay, so yes, indeed, that is x. Your development of the geometric eye. Okay, so that is x. That is x. 1 down, 2 to go. We need 3 others. We need 2 others after this. We've gotten B4. Angle E equal to A to X angles in the same segment. Okay, now Star Christie, in order for us to be saying that, okay, we need to check 1, 2, 3, 4. Are they all at the circumference of a circle, right? Because remember, you know, if this and that, they were at the circumference of a particular circle, then we could say that this is equal to that for the reason that you've mentioned. But unfortunately, okay, another thing would be, would have to prove, okay, if you could prove that BOEA is a cyclic chord, then you could say that that angle and that angle are equal. But unfortunately, you know, at this current moment, it ain't the situation. Okay, let's see. Kid Lash says angle A is equal to B4. Reason, corresponding angles. Wow. Are we clapping again for Kid Lash? This line is parallel to that one. So our F shape, this bottom of this parallel line, bottom of that parallel line on the same side of the transversal line. Okay, so bottom of this line, bottom of that line. Now, if we look at the reason that has been given, it makes perfect sense and it's correct, right? So, yes, sirree, indeed. So far, we are saying angle E is equal to X is equal to angle B4. What was the reason? We had said tan chord theorem. Okay. Then, now, Kid Lash is saying to us, angle A is equal to angle B4, which is equal to X. The reason that he's saying that is and this is important, guys, that we write the reasons as per the acceptable reason document. We say correspond angles, then we state the parallel lines. The lines, guys, that were parallel, remember we were told here that BD is parallel to AO. So we write that BD is parallel to AO. And this is very key, that your reason must be, you write for angles, for parallel lines, you always write whatever it is, corresponding angles, then you must state the lines that are parallel. Guys, if you are careless and you state corresponding angles without stating the lines that are parallel, you will lose marks. You will lose marks. And it will be unnecessary for you to be losing marks because you did not state the lines that are parallel. So you can't omit this part, all right? Yeah, because the corresponding angles are there despite the parallel lines, but the angles are equal as corresponding angles because of lines that are parallel. So you must state this. So we've got one more. So I've got an X there, and every time I get an answer, I fill in my diagram. Got an X there, I've got an X there, I've got an X there. Now I need one more. One more to go, one more to go. We got one more, guys. Anything else that's coming to mind? I love this. I love this. I love the fact that people are just. Kid Lash seems to be having a very well trained geometric eye. I am beginning to wonder if Kid Lash is actually a student. Maybe Kid Lash is a former student who used to be good at this thing, operating under a different name, alias. You know, maybe he will reveal the truth to us. You know. Or maybe a tutor or a teacher or something, you know. Seems like he's finding the answers all too easily. Jonga, do you see this? Do you see what I'm saying? Kid lashing us here. Okay, what about angle 01, Mr. Kid? What sayest thou? Sorry, my bad. I was like, what about angle 01? I was very curious there for a moment. Gilunga says B2. What is it? B2. Isosceles triangle. Okay, I see what you're saying, Kilunga, but after having said that, what are you saying to me? Kumalo is then saying OB is equal to OE, right? But remember, guys, that's not the full-on reason. You remember that if you say B2, there must be a reason that is very much key. B2, right? B2, I agree, is equal to X. Why? All right. Isosceles triangle doesn't fly. All right. It wouldn't be a reason that would hold water. You wouldn't get marks for saying isosceles triangle. So try again. Kumalo says OB is equal to OE. And then you need to further underscore that by saying angles opposite equal sides. Thank you so much. Thank you so much. Kumalo, you have now obviously solidified your place as one of angles opposite equal sides. So yes, 100% straightforward, to the point. That's 100% correct. Okay. All right. Good people, I unfortunately have to end right here with my live. But if you guys want to just screenshot this, I have to end right here because it is time for me to actually, it's 10:30 now, at least my time from my side. And I have to vamos. And I know maybe you're enjoying it, you're having fun, but unfortunately, this is where I come to an end. When are we going live again, Natalia? We will try and actually, you're a former student, Kid Lash. I knew it. I was like, this guy is just doing the things. No, that's fine though. Thank you for actually coming through into the live and just, you know, that means you really loved the maths then back in the days. Mind telling us you got an A in maths? How long ago was this? Kid Lash, let's lash the kid here. Oh my soul, you don't have privileges of actually going live with someone. It would be nice to have a chat with you, but I guess it's fine. 2024, nice man, that's awesome. And currently, what are you doing? What's Kid Lash up to at the moment? So Natalia, let's I'll see you guys tomorrow again, same time, which is roughly did the live at 8:30. Let's see each other tomorrow at 8:30. Mechanical engineering, Kid Lash, good. That's neat, man. Proud of you. Proud of you. Keep up the good work, buddy. And are you? I mean, are you enjoying it? Is it difficult, hard, loving it? Yeah, let's see each other tomorrow, Natalia. How many of you guys actually here in the comment section are actually grade 12? Just let me know. And how many of you are actually grade 11? If you can just let me know. Yes, Lou, we can continue with the same topic. I think let's continue. Oh, Lunga, in 2015, my man. Well, thanks, bro. I really appreciate I appreciate the positive messages there. Respect for what I do. Thank you. Really appreciate it. You have no idea. Star Christy, you're a star. Thank you so much. It was great. You were epic as well. Thank you for actually answering and stuff. Natalia, you're upgrading. Nice. No problem. So that means you're writing end of this year, hey? November. Well, yeah, let's get cracking then, eh? Let's get cracking. We'll push it from here. Kumalo, grade 11. Nice. Great having you then. Homo, so you're doing grade 12. Nice. Awesome. People wanting to make a glorious comeback in September trial exams, doing the most. I hope you guys are really like fired up about like killing it, doing the I don't know why I use that word all the time. I'm just afraid that it will just, the algorithm will pick this up and just like end my life because of that. But thank you so much, man. Good night, Lou. Have a good one. Thanks for being here. You guys made the lesson quite fun, I must say. You made it worth it. Very much worth it. Terina Nyondo, 12. Yes. Okay, awesome. I really learned a lot from your live. Thank you. Lisa 10, you're phenomenal. Lisa 10 was the one that answered with whatchamacall was we were asking, alternate the completing of the statement. Yeah, good on you. Good on you. You keep it up. Lisa, you're in grade 12. Lisa? Why do I have a feeling you've actually you completed, right? Lisa, are we also in grade 12? You didn't answer in the comment section. I'm like noting what everybody's saying here. Grade 12, grade 11. You learned a lot from me. Thank you. Oh, you're doing grade 12. Okay, that's awesome. Okay. Thank you so much for investing your time in helping us. You're welcome. You're welcome. It's a joy. It's really like it's a passion. It's a passion project if you want. It's a passion project. So we'll pick it up, guys, from here. We'll just push it with the geometry and just see what other exciting things we can do here with the geometry next time. But unfortunately, I have to bounce right now. Yeah, the grade 12 as well, which is fun in the sun, proving of the theorems. You know, guys, proving of the theorems, something that really is common in similarity. Yeah, we can have fun with that. Fun in the sun. Okay. Good night. Thank you. And thank you for the gifts, Natalia. I really appreciate the gifts as well. Thanks a ton. You guys take care, and I'll see you